Hey, welcome to our first official lesson of Chapter 4. Chapter 4 is all about curve sketching. So in this chapter, we're going to be looking at what the first derivative and what the second derivative tell me about the graph of a function. So we're going to do a little investigation first. On the left here, I've got two graphs on the same grid. The red graph is the original function. And when I take the derivative, I know that the equation, I'll get 3 times a third, that's just 1, so I now have a 1 for a coefficient, times x squared. And then the derivative of the second piece will be 2x, and then the derivative of the third piece will be negative 3. So we haven't done this before, but we're going to take a look at the original graph, which is the cubic in red, and the graph of the derivative on the same grid. And I want to know, how are these two graphs related? So in some of the questions below, I'm going to be asking about f of x, and sometimes I'm going to be asking about the derivative. So you just have to kind of think about, well, which color are we looking at? So in the first question here, we're talking about the red graph, the original f at x, and it just says over which intervals is f at x increasing intervals. And there are two here. There's two intervals, so you can put the x in front if you like, but it's not required. When I talk about increasing and decreasing, I'm always starting on the left-hand side of my graph and just kind of tracing along the curve and seeing, am I going up or am I going down? And so when I start off, I'm increasing until I get to negative 3. So my first interval of increase starts at negative infinity, and it goes until negative 3. After that, I'm decreasing, which is actually part of the Part B question, so I'm going to move over here for a second. After negative 3, I start decreasing or heading down until I get here where x is equal to positive 1. So my first interval of decrease starts at negative 3 and goes to 1. And so sometimes we just put this x belongs to in front to remind us that this is not a point. It is in fact an interval of x values all the way from negative 3 to 1. Notice that I'm using round brackets here and round brackets over here, and that means that I'm not including the value negative 3 in either interval. And that's because if I'm actually right at negative 3 and I pause there just for a second, I'm neither increasing nor decreasing. You can't really tell, right? It's the end of the increase and the beginning of the decrease, so it's neither. All right, and we left off at x equals negative 1, and then after that the graph starts to increase again, and it's going to increase to infinity. I know that because it's a cubic graph, right? So this actually would have arrows on the end, and I'm heading up forever. So my second interval of increase, you can either use a comma or a union symbol here. We're going from 1 up to infinity. All right, so, and then there are no more intervals of decrease. That's it. We're done there. All right, Part C is saying when f at x is increasing, what do you notice about the graph of the derivative? So it's asking you, go and look at these two intervals on the blue graph, and what do we notice? So going from negative infinity to negative 3, I'm just going to highlight that section of the blue graph. So we're looking at this part here, okay? And then we're looking from the interval from 1 to infinity. So starting at x equals 1 on the blue graph, we're going to be looking at these two sections and asking ourselves, well, what do we notice here about these two? And then in Part B, I'm just going to skip ahead for a second. I'm going to use a different color here, even though I'm still looking at the blue graph. So I'm looking at the blue graph, but I'm going to use green here. And this one's asking me, when the original function, the red graph, is decreasing, what do we notice about the derivative graph? So the original function was decreasing from negative 3 to 1. And so I'm going to go to my blue graph from x equals negative 3 to 1, and I want to notice what's different about this section of the derivative graph. And so what I notice is when the original graph was increasing, my derivative graph is above the x-axis. And same thing over here, when I was increasing on this portion of the red graph, my derivative graph is above the x-axis. Now, for the middle piece here, what I notice is on my original graph, when I'm decreasing on my original graph, the derivative graph is below the x-axis. Now, we don't like to use words a lot in math, so we're going to try and transform that into symbols. Instead of saying above the x-axis, I'm going to talk about, well, what's going on with the value of the derivative. So what that tells me, if I'm above the the x-axis, the value of the derivative is a positive number. So the value of the derivative is going to be some positive number greater than 0. And below the x-axis, again, I can transform that into some mathematical notation, and I can say that the value of the derivative is going to be below 0 or negative, like this. And so we're going to use this idea to help us come up with the sketch of the curve. So, and we call this the first derivative test to find intervals of increase and decrease. So it's going to help us, or sorry, this isn't the first derivative test. I'm going to teach that in a minute. We're going to use the first derivative to find intervals of increase and decrease. So if I have a function that's continuous and differentiable, that means I can take the derivative on some interval from a to b, and I can either be including the endpoints or not. So there's no gaps in that graph from a to b, and it's differentiable there. If I find that the derivative is positive, then what I know is that the original graph is increasing. If I find, on the other hand, that the derivative value is a negative number, then that tells me that the original graph is decreasing or heading down on the graph. So that's going to just help me figure out, right, if I wanted to know what's happening on a certain interval of values, I can just find out, well, what's the sign of the derivative there? All right, so our next example, this is example 2, it's because I removed example 1. So, whoops, we're starting with 2. We're going to make a rough sketch here. So what that means, when I do a rough sketch, I'm only including relevant values on my scale. There we go. And so we've got some function f. We know it's differentiable. They're telling me that. And it's going to satisfy the following conditions. So we're going to do this twice, 2 different graphs. In graph A, what I know is that the derivative is increasing when the x value, sorry, I'll use a different color highlighter because we just used that one. The derivative is the derivative is positive. So the derivative value is positive when the x values are negative. So that tells me that, remember, when the derivative value is positive, that tells me that the graph is increasing, and it's going to be increasing on this interval here. So if my x values are less than 0, that means that I'm over on the left-hand side of the axis over here. The graph should always be increasing or heading up. And then what we find after that is the graph is decreasing because the derivative value is negative. Remember, the negative derivative value tells me the original graph is heading down, and that's happening when x is greater than 0. So I'm decreasing on this interval here. And then the third piece here, when they tell me that f at 0 equals 4, this is just a point on the graph. And remember, it's normally f at x, so our x number is 0. And we're saying that the value of the function when I plug in 0 is 4, so that's the y value of the point. So whenever I'm given a point, I always start with that on my graph. So I'm going to head to my graph, and I'm going to put a point at 0, 4. So I'm adding that number to my graph because it's relevant. And then the only other thing I need to make sure I do is increase when the x values are negative. So I should be starting low and heading up to that value of 4, and then decreasing when I head into the positive x values, so heading down. And there are multiple ways this graph could look. I've kind of drawn it like a lopsided parabola. It could be a perfectly even parabola. It could be an absolute value function. I would be increasing then, and then heading down, decreasing. The only reason I know it's not an absolute value function is because they told me that f is differentiable, and that would mean everywhere. And an absolute value function is not differentiable at its vertex point. Another way that this graph could look is I could be heading up into 4, and then I could be curving down into a horizontal asymptote, maybe on the right-hand side. I don't have enough information to draw just one graph here. All right, moving on to graph B. This time I have that the value of the derivative is positive when the x values are less than -1. So again, this is telling me that I'm increasing right? If the derivative is positive, I'm increasing on this interval and on this interval. So I have two intervals of increase. So 2 times I'm heading up, sort of like our example up here, right? I was heading up, paused, and then heading up again. All right, then the next part tells me that the derivative value is negative. So that means that I'm decreasing when I'm in this range of values. And then again, that last point, this last piece of information here is just a point. They're telling me that the x value is 0 and the y value is also 0. So again, I'm going to start with a rough sketch of my graph. That was bad. Okay, so I know that there's a point at 0, 0. I always start with those given points if I can. And then I have a few values here of interest. X equals -1, they've told me it is a point of interest, and x equals 2 is a point of interest. So those are the only numbers that I need to include on my sketch. What they're saying is I'm increasing until I get to x equals -1. Now I don't know how high that goes, so perhaps there's a point up here above -1, and I'm coming in and I'm increasing until I get to -1. And then between -1 and 2, I should be decreasing, and I need to pass through this point here. And so maybe it comes down to a point down here. I'm going to decrease until I get to that point. And then it tells me now your graph is going to start increasing because the derivative value is 0. Remember that the derivative tells me the slope of the graph. So this makes sense. When the slopes are positive, I'm going to see an increase on my graph. So positive slope, positive slope, positive slope until I get to -1. And then I start getting a negative slope here of my tangent. And then again, after 2, another positive slope. I don't know how high or how low these points are. This is still a bit of a mystery, and we're going to work towards that by the end of this unit. All right, example 3, the following graph represents the derivative function. So this time they've given us the derivative, and there are little arrows at the end of this. We don't know what the original function looked like. So what I'm going to do is kind of piece together what can I figure out about the original function. So I want to know where was the original graph increasing. Now remember from our definition in the box on the first page, increasing means that the value of the derivative or the slope of the tangent is positive. So for I'm looking for where is the value of the derivative positive. And remember, this tells me the value of the derivative. This is the derivative function. And so here, the value of the derivative is -2, and here the value of the derivative is -3. I'm talking about the heights when I talk about the value of the derivative. And so once I get to x equals 1, the value of the derivative starts increasing above y equals 0. So the value of the derivative is positive after x equals 1. And you can use interval notation here, or you could just say x is greater than 1. That's fine too. And then the second piece is asking us where is the value, or where is the original graph decreasing? Now remember, we can relate that to our derivative graph. If the original graph is decreasing, then the derivative is negative. So that's what I'm looking for here. So looking over at my graph, where is this graph negative? So where is it below the x-axis? That's this whole stretch here. And so it's anything less than 1. And again, you could write x is less than 1 there. All right, now the third part is asking me, well, where then are the local extrema? Remember, that means maximums and minimums. So I'm looking for where might the maximums and minimums be. Well, you can start to kind of put this together here. The graph is increasing when x is bigger than 1. So the graph is like heading up over here. So maybe it's like heading up like this. And then over here, we said the derivative value is negative. So the graph must have been heading down like this. at x equals 1, it says here that the value of the derivative is 0. Well, that means that the slope of the tangent is 0, and that's going to mean that I have a local minimum there. And so that's our local extrema. So when they ask for local extrema, they're actually asking me, where is the value of the derivative equal to 0? All right, now I've drawn on this graph, but actually in part B, they've asked me to draw a very specific version of the graph. It says this time, assume that f at 0 equals 3. So I know in part B then that I need to have a point at 0, 3. So I'm going to erase the work that I've done so far, or if you've already got this, you can just draw a second graph and label them. Label the one with B. We're going to go to 0, 3. There's our point. And now I'm going to use those same ideas that we had before. The graph should be increasing after x equals 1. I know that I have some sort of minimum point at x equals 1. I should be decreasing at the beginning and then increasing coming out. Now I don't know how low this minimum point is, so I'm just going to throw it on here. There are other things that we could do to figure it out, but that's all I'm looking for in this type of question. All right, we're going to use the algebraic method for using the first derivative to find the intervals of increase and decrease. So what happens if I give you an equation? How are you going to figure out where is the graph increasing or decreasing? Well, the first thing we're going to do is find the first derivative. Then we're going to set it equal to 0 and solve for x. We're also going to find the x values where the derivative or the original function does not exist, because those are important to us as well. Then we're going to make a chart with rows including all of these x values that we just found out. With columns for all of those x value intervals. And then down the left-hand side, we'll have a row for test point, the sign of the derivative, and actually what's happening on the original function. And then, of course, we'll write a summary sentence where we talk about what did we figure out. All right, so you're not going to have room for both of these questions on this page. You'll have to grab some extra paper for probably part B. In part A, we're going to start by taking the derivative. So what we have here is a product rule. I have something with x's times something with x's. So like this guy is u, and this guy is v, and I'm thinking about the product rule, remember, is u prime v plus u v prime. And I'm going to take the derivative of each piece. So the derivative of the first bracket, I bring the 3 out front. Remember, this is the power of a function rule, or the chain rule. So I'm taking the derivative just of that outer power. I bring the 3 out front, subtract 1 from the exponent, and then I take the derivative of the inner bracket, and that's just 2. So now we've got u prime. We're going to move on to v. So I'm just copying down the old v bracket, and then I add. Now I'm going to take the original u bracket and multiply it by the derivative of v. So again, we've got a chain rule here. I'm going to bring the 2 out front, multiply it by the original bracket, but subtracting 1 from the exponent, and then taking the derivative of that inner bracket. Now, I know from the algorithm above that I want to set this equal to 0 and solve. So I can throw the 0 in here at any point. If it helps me remember my goal, I might put it in right away. If I want to set it equal to 0, what I need then is a factored expression. So I'm not going to expand this out. I'm going to try to factor it. So what I might do first is just reorganize. So I see here that I've got 2 multipliers. I'm going to bring them to the front and say that this is 6 times the 2 brackets. And then over here, I see I've got a 2 and a 2x. Again, I'm going to bring those both to the front. So I've got 4x when I multiply them together. Okay, so it's looking a little nicer. But now again, I want to factor, not expand. So I'm going to be looking for common factors in each piece. So first I just look at the coefficients. So I've got 6 and I've got 4. And I'm asking myself, well, what's the biggest thing I can divide both of those by? And it's 2. And then I look at the next piece. Now the next piece is the x, but there is no x over here. So I can't take out a common factor of x. It's just left over. And then I start looking for matching brackets. So I've got a 2x plus 3 and a 2x plus 3. There's 2 of them here and 3 of them here, so I can take at least 2 from each one. And then our last matching bracket is x squared plus 3. There's 2 of them here, but only one of them here, so I can take 1. So now that we've decided what we're going to divide by, we're going to take each of our original terms and divide by this. So 6 divided by 2 gives me 3. And then when I divide these brackets, there's the same number of brackets, so they will come out to equal a multiplier of 1, but I won't write that. And then this bracket, there were 2 of them, I divided 1 away, so I'm left with 1 of them. And moving on to our second term, I've got positive 4 divided by 2, so that's positive 2. And then the x, there is no divisor of x, so the x is still there as a multiplier. Then our 2x plus 3 bracket, there were 3 of them, I divided out 2 of them, so there's 1 left over. And then the x plus 3 divided by x plus 3, that leaves me with just 1. And I'm all done. So we're on our way. Remember, we want this to be a bunch of factors being multiplied. We've got a nice kind of start here, but we're going to try and clean up this last bracket. At this point, there are no common factors in that last bracket, so I have to expand before I can try to refactor it. So I expand all of that out, and now I'm going to collect like terms and see if there's a common factor or another type of factoring I can do. Okay, so there's no common factor, and at this point what I do have is a bunch of brackets multiplying together to equal 0. So I can separate them out and I can try and factor this later, or you can try and factor it now. So I'm going to separate it at this point. There are 4 things being multiplied to equal 0. One of the 4 things has to equal 0. Now 2 is never going to equal 0, so we kind of usually ignore him. So I'm going to start with the first bracket here. So I've got 2x plus 3 has to equal 0. Now you can keep the squaring if you like on that bracket, but then you're going to square root to move it to the other side, and the square root of 0 is still 0. So I'm fine if you skip that step. And then I'm going to isolate for x here. So I'm going to bring the 3 over, it becomes negative 3, and then I'll divide out the 2. All right, moving on to the second bracket. We've got x squared plus 3 equals 0. You might be able to see right away there's no solutions to this. To prove it, I'm going to bring the 3 over, and then when I try to take the positive and negative square root of negative 3, there are no solutions to that. Another way to think of it is, and you could write a little sentence describing this is a parabola that opens up and it's been shifted up 3, so there are no x-intercepts. This guy will never equal 0. And then our third bracket, where does that one equal 0? Well, I kind of have a suspicion here that there's no solutions, just because they're all positive. I'm wondering if this is also a parabola that opens up and has been shifted up that doesn't actually touch the x-axis. So to prove that, I'm going to check just the discriminant part of the quadratic formula. If you forgot about this, then you would just go ahead with the whole quadratic formula, and you're going to end up with the same sort of problem here. Remember, this is the piece under the square root that I'm investigating. And what I get here is 36 minus 252, which is a negative number. So this is less than 0, so I'm going to try and square root a negative number, which again, just like over here, is going to give me no solutions. So whenever I check the discriminant and I get a negative number, that tells me there's no solutions. All right, so I really only have one x value that I need to worry about here. I'm just going to scroll back up, like, what are we even trying to do? Do you remember? We found the derivative, we set it equal to 0, we found that x value, and then we also need to look for the x values where the derivative or the original function does not exist. Now this original function is a polynomial function, right? So this one is actually like a power of 7 polynomial. A polynomial function exists everywhere. And then the derivative as well, when I take a look at this derivative, it's also a polynomial function, so it exists everywhere. So I only have to worry about this x value here. I'm going to create a chart. Above it kind of lists out, but your chart is going to have the x intervals across the top. And then there's going to be a row for a test point. And then a row to tell me what is the sign of f prime of x. You can actually find the actual number if you want, but I only need you to record the value. Is it positive or is it negative is all I care about. And then the last row is going to be to talk about the behavior of f at x. What's the graph look like? All right, now across the top here, we're going to have our intervals. We're always going to start at negative infinity for graphs that have a domain of a set of real numbers. And then we're always going to end at positive infinity. The only x value that we have to worry about here is negative 3/2. And so that is the only stopping point in my chart. I just need to think about what's happening before negative 3/2, what's happening at negative 3/2, and what's happening afterwards. All right, so we're going to go through, I'm going to pick a test number somewhere between negative infinity and negative 3/2. I can pick any number. You can pick negative 1,000 or negative 10. Negative 2 would be maybe like probably the biggest number that you would pick. You cannot pick negative 3/2. It's not actually in the interval because it's a round bracket. So I'm going to pick negative 10, and I'm going to go back up here to my factored version of f prime at x. I had not divided anything over across the equal sign, so this is actually f prime at x here. And I'm going to imagine, well, what happens if I were to put negative 10 in each one of these factors? Well, the first factor is 2, which is always positive, and I'm only going to write down the signs here. The second bracket, if I put a negative 10 in here, I would get negative 20 plus 3, which is a negative number, but I'm squaring that. And then in the third bracket here, if I put negative 10 in, I would get negative 10 squared, which is positive 100, plus 3. So this is a positive number. And then in the last bracket, if I put negative 10 in here, and this is where you might want to check on your calculator, you're going to get negative 10 squared, which is 100, so 700, minus 60 plus 9. And altogether, that's going to come out to some positive number. And again, I don't actually care what the number is. And now I'm just going to ask myself, well, what do I get overall then? So I've got a positive times a negative squared, that's a positive, times a positive times a positive. So that altogether is a positive number. Again, if you want to double check by plugging negative 10 in there, you can do it and just make sure you get a positive answer. I would like to see you reasoning through, though, the sign of each factor when it's a polynomial like this. And then we're going to ask ourselves, what does that tell me about the actual graph? If the derivative is a positive number, that tells me that the actual graph is increasing. And I know that that's going to be true for any number I pick in this interval. I'm always going to get a positive derivative, and so the graph is always increasing from negative infinity up to negative 3/2. Now at negative 3/2, I don't need to pick a test point. This is my test point. And I don't really need to worry about the sign of f prime at x, because we said, actually I got this number because I know it's going to make the derivative equal 0. So I've already done the work there. And what that tells me, if the derivative is equal, if the derivative value is equal to 0, then that tells me that the slope of the tangent is 0, which tells me that the graph must be flat at that point. And then looking in our last interval, I'm going to pick some number between negative 3/2 and infinity. So I'm going to pick 0, and I'm going to plug that again into my simplified derivative function. I have not moved anything across the equal sign. This is the whole derivative. So again, going through each of the factors. 2 is positive, and then plugging 0 into this bracket, I'm going to get positive 3, and it's squared. And then plugging 0 into this bracket, I'm also going to get positive 3. And then plugging 0 into this bracket, I'm going to get 0 plus 9, so another positive. And when I multiply these things all together, I am going to get a positive, right? It's all positive numbers being multiplied. And again, if the derivative value is positive, that tells me that the original graph is increasing or heading up, or maybe you could think of it as it has positive slopes. And so then I'm going to write a therefore sentence to summarize what I found. Don't forget about this piece. I do want to see if you can put it all together and tell me what you found out about the original graph. Even though it's kind of in the table here, I want to see you connect this word increasing with the interval at the top. So a couple notes on communication. You don't have to include the X belongs to, that's fine. You can use a comma here or a union symbol, that's fine. And then just a note, this here, going from negative infinity, pausing at -3/2, and then restarting, this is not the same as negative infinity to positive infinity. We are not including -3/2 here, so that's important that you know that these things are not the same. All right, I'm going to pause the video here and then we'll finish up the last example.